Okay, welcome back. In this video, we're going to talk about centripetal acceleration. It's a little bit different than just regular acceleration that we've talked about so far in the class. So, if you're watching the video, be following along with your guided notes. There's a little bit of a section here to fill out as we go through these slides. Okay, so it says here on this slide that there's acceleration on a circular path at constant speed. That doesn't really make sense to us, does it? How can you have acceleration when you're moving at a constant speed?
Changing direction.
Good, you got to change directions. And that's what centripetal acceleration is. And so there's a picture of this guy, looks kind of like Dalton. Swinging this looks like a ball tied to a string around his head. And so this ball is changing direction. So even if he swings it at a constant speed, it's going to be accelerating because he's changing directions. Remember, if you change directions, you're changing velocity. So, all right. So let's get into it. So even though the ball above, so it says even though the ball is moving around at constant speed, its velocity is changing because it's changing directions. And so that's how you get acceleration at a constant speed. You just got to change directions. So since velocity is changing, so does acceleration. There's a lot of examples of this in the real world. One is a car moving at a constant speed around a turn. So when you're in your car, maybe you're going 30 miles per hour, but you're turning. You're going to be experiencing centripetal acceleration. Or there's satellites that orbit the Earth. The satellites are moving at a constant velocity, but they're always changing directions, obviously, as they orbit the Earth. So we're going to talk a little bit about how to find the magnitude of centripetal acceleration and also how to determine its direction in the coming slides. Okay, so there's a spot for you to write the definition for centripetal acceleration. Let me give you a second to write that down. Okay, so if we look at the definition, it says centripetal acceleration is the center-seeking acceleration of an object moving in a circle at constant speed. So I like this definition. It says that it's the center-seeking acceleration. So I want to talk about this diagram right here for a second, guys. So look up here. Let's just assume this red dot is a car that's going around this circular track. Okay, so it's going around this track clockwise. If you wanted to draw the vector for the centripetal acceleration, the vector always points toward the center of the turn. So this vector right here, we would put AC, that's centripetal acceleration. So A sub C is centripetal acceleration. So if the car made its way over to here on the track, how would you draw the vector for centripetal acceleration? Well, it points toward the center again. Okay. What if the car was right here? Again, that centripetal acceleration points toward the center of the track. However, if you look at the velocity of the car can be thought of as at a specific moment in time, which direction is it going? So if you froze time when the car was right here, which way would that car be going? It would be going off in a direction like this, right? What about at this point? So that would be its velocity vector. What about at this point right here? So imagine a straight line coming through. The velocity vector would point right there. And if we were going to draw the velocity vector right here, straight line from where its current position is. So a little bit different velocity vectors and centripetal acceleration vectors. Okay, when we're finding the magnitude of the centripetal acceleration, we're going to use this formula. It's one of the very important ones for this chapter. So A sub c means what, guys? Centripetal acceleration is equal to v. What do you think v means in this case? Velocity squared divided by r. What do you think r means? Yeah, it's the radius of a circle. And let me go over what radius is for a second, okay? Radius is from the center of the circle to the edge of the circle. That's the radius. It's a distance from the center of the circle to the edge of the circle. Now, a lot of students will get confused with diameter. Diameter measures all the way across. So if they give you diameter, how can you find radius? Divided by 2. So radius is equal to diameter divided by 2. Okay, the centripetal acceleration vector always points toward the center. We talked about that in this diagram here. It always points toward the center of the circle. Its magnitude is equal to the square of its velocity or speed divided by the radius of the turn. Okay, I've got a couple of, 3 practice problems, number 12, 13, and 14, and then we'll be finished. Okay. So practice problem number 12, it says a 1,000 kilogram car moves with a constant speed of 13 meters per second around a flat circular track of radius 40 meters. What is the magnitude and direction of the centripetal acceleration? So we want both the magnitude and a direction for the centripetal acceleration. Okay, how do we find the magnitude, guys? What's that formula? AC is equal to what? V squared over R. Thank you, yeah. So now let's just plug in the numbers. Did it give us centripetal acceleration? Nope, that's what we're supposed to find. So I'm just going to keep it A sub c. Did it give us velocity? Yeah, 13 meters per second was its velocity, so 13 goes here. But students always forget this part. They always forget to square it. Okay, so don't forget to put the square there. Divided by, what's the radius? Did it tell us?
40.
The radius was 40 meters, so we're just going to put 40 down here. 13 squared is what, guys? 169, thank you. So 169 goes on top, and then divided by 40. 4.23. Okay, what is our units going to be for an acceleration? Meters per second squared. Okay, very good. That's the magnitude. Now, what would the direction? What could we say about the direction? Which direction would this acceleration vector point? Could we just say toward the center of the track? Didn't really give us a picture, so I'm just going to put toward the center of the track. Okay. Now here's something that I just noticed. Why did it give us the mass of that car? Did we use it? No. We look at our formula here. There's nowhere for mass. So sometimes in these problems, they'll give you information that you just don't need. It didn't matter how massive that car was. So, okay, did we get the right answer? 4.23 and toward the center of the track. Yeah. Okay, practice problem number 13. It says a ball on a string is spun at constant velocity of 11 meters per second. So you have this ball on the string and you're spinning it. Okay? It says, what is the acceleration if the distance from the hand to the ball is 1 meter? Then it goes on and says, what is the acceleration if the distance from the hand to the ball is 2 meters? And it ends by saying, where is the acceleration more with 1 meter radius or 2 meter radius? You guys have experienced this. You've always spun something around your head. Make a hypothesis here. Which one's going to have a higher centripetal acceleration? When the radius is 1 meter or 2 meters?
2 meters. 1. 1, because you divide by a smaller number.
No, 2 because it has to make the same distance around the same amount of time.
But okay, Rylan, I see what you're saying. Rylan, you're right, but you're spinning it at the same speed.
Yeah.
Things farther away from the center move faster though, like if you're
So you're spinning it at the same rate.
It's moving at the same speed regardless of how far which one accelerates.
So if the circle is smaller than it would be.
Good, Ryan, I know what you're thinking. You're right, what you were thinking, but now you just have to say we're moving at the same speed. So let's put it in the formula and see. Okay? Now with physics problems, guys, I always like to draw a picture. So draw a picture of Dalton here. Okay, and he's got his hand right here, and then you got a 1 meter string, and then there's a ball on the end, so 1 meter. Okay, he's spinning it around that 1 meter.
The head's not big enough.
It's too tall.
Sorry, I'll modify it next time. Okay, so there's our picture. Let's figure out the magnitude of the centripetal acceleration. Centripetal acceleration is equal to what, guys? What's the formula? E squared over r. Now let's plug it in. What's the velocity that he was spinning it? 11 meters per second. Yeah, it told us in the problem. So 11 goes in for v. So 11, don't forget to square it, divided by what's the radius? 1. Okay, what's 11 squared?
121.
121 divided by 1 is still 121. So what's my units going to be? Meters per second squared. Okay, so that's the magnitude of the centripetal acceleration if it's 1 meter in radius. Okay, now let's draw Dalton again.
There you go. Arm is way too long.
But now it's 2 meters.
How come my arm's longer than my body?
Yeah, I don't know. It's not to scale. Again, he's spinning it around the 2 meter radius. Let's find out what the centripetal acceleration of this scenario would be. Okay, so what's the velocity still? Still 11. We're going to square it. What's the radius this time?
43.
2. So we get 121 divided by 2, which is what? 60.5 what?
Meters per second squared.
Meters per second squared. So you'll notice that as you pull this ball, it has a smaller radius. It goes at a much faster centripetal acceleration. Have you ever seen those figure skaters? And they're holding their hands out. I know you watch figure skating, Dalton.
Always, they're hot.
Okay.
That's why you watch it too.
Do they spin faster when their arms are out or in?
In.
And that's why, because the radius is much smaller. So you divide by a smaller number. Okay. Did we get the answers right? Yeah. Okay, last practice problem. This is a good one. It said, assume that the Ferris wheel shown below is spinning clockwise. Okay, spinning clockwise. So make a note of that. It's going this way. At each point labeled A, B, C, and D, it wants you to draw the velocity and the acceleration vectors. So let's do that. At point A, B, C, and D. And this is the velocity vector and the acceleration vector. Okay. Let's just start at A. Again, it's moving up and it's going clockwise. So which way would the acceleration vector point? Acceleration. Always points toward the center of the circle. So on A, the acceleration vector is going to point toward the right. What about its velocity vector? Now think about velocity as the direction it's moving at that moment in time. Which way would it be moving at A? Straight up. Yeah.
Straight up.
Straight up. Straight up.
Straight up G.
Okay.
Actually, straight up at A.
Let's move to B. Okay, let's do velocity vector first. Let's figure out what goes with the velocity vector. Which way is it moving at that moment in time? To the right, yeah. Because it's going clockwise, it's going this way. At that moment, it's if you drew a line here, it would be going straight to the right. So velocity is straight to the right. What about its acceleration vector? Down. Okay. So take a second and finish up C and D. If you're watching the video, hit pause and try C and D. Okay, let's see if we got C and D right. What did you guys put for a velocity vector at point C? Straight down. Okay, so velocity would be going straight down. What about its acceleration vector here? Yeah, toward the center, so it's got to be pointing to the left. Okay. Now just point D left. Again, it's going clockwise, so it's going this way. At point D, which way is the velocity vector going to point? To the left. And what about the acceleration vector? Straight toward the center, so it's got to go straight up. Okay. Well, hopefully that helps you kind of understand how to find the magnitude of centripetal acceleration and the direction that we draw the vectors. Okay, guys, we've learned enough to do a worksheet in the student workbook. The worksheet that I would like you to complete right now is called Centripetal Acceleration Worksheet. So we'll take a second, turn to that page, and we'll get that done.